This is level 1 of the CFA program, the topic on quantitative methods, and the reading that serves as an introduction to linear regression. Of course, in our study of quantitative methods, we're trying to determine the relationship between two variables. And of course, the starting point is always the correlation coefficient. We want to know if two variables are highly correlated, lowly correlated, or not correlated at all. But of course, correlation does not imply causation. And so we move one step further to this concept of linear regression. What we're trying to do here is determine not only whether or not there is a relationship between two variables, but if one variable has an impact on another variable. And so, of course, let me go ahead and start with the definition of linear regression. Let's take the first word there. Linear implies a linear relationship between those two variables. Now, of course, relationships between and among variables can take on many forms. One of them is a linear relationship. So that's the first part of this definition. The second part is the term regression, which I always found interesting as an undergrad because it sounded to me like regression means going backwards. But then as I got into graduate school, I learned, and a history lesson is probably relevant here, that back in the early 1800s, there was a scientist who was studying genetics and determined that there was some regression to the mean in terms of the height of children once they reached, full-blown maturity. And so it was this regression to the mean. And that's exactly what we're trying to do here. We're trying to take two variables. And so imagine a plot, on a graph with all these different points. What we're trying to do is squeeze them into their mean. And that's what regression means. And you'll see that as we go through the learning objectives. Take a look at those first three learning outcome statements. We want to describe a regression model, talk about dependent and independent variables. And this is what I was suggesting in that first slide about one variable impacting another variable. What we're going to do is describe this least squares criterion to estimate some regression coefficients. And then that's probably the more important part of that second LOS is the interpretation of it. Of course, we need to know assumptions of the model. We need to know about residuals. And then look at that fourth one there, coefficient of determination. This is going to be R squared. We know what R is. R is the correlation coefficient. So we're going to square it, and we're going to have to interpret that as well and see how that fits into an F-statistic, an analysis of variance. And then we'll do some predicted values and maybe a confidence interval. And then we'll end with some different functional forms. So let's go ahead and take a look at a brief recap of what we ought to know about quantitative methods and correlations and regressions. All right, so that first bullet point there. The regression model attempts to predict the value of a dependent variable based on the value of an independent variable. All right, so we have two variables now, not just two, but we have identified one as an independent variable and then one as a dependent variable. So of course, the dependent variable depends on the independent variable. And of course, we're assuming a linear relationship between the two. What we're going to try to do is predict the dependent variable based on the performance of the independent variable. And so there are some other terms for the dependent variable: predicted, explained, and the endogenous variable. And that's always the y. The independent variable, on the other hand, it explains the variation in the dependent variable. It's also called explanatory and predicting, or the exogenous, and this is always the x. Let me give you a little quick reminder that if you're ever on an exam and you need to know which one is which, endogenous or exogenous, just remember x has an x in it. And you'll never have to try to figure it out on an exam. That's one of those short memory buttons. Let's take a look at that first LOS. Describe a simple linear regression model. And of course, you did this in your younger days. Y equals A plus BX. So that's the same model that we're using today. But of course, in quantitative methods, we use a little bit fancier notation. So notice there are a couple of betas in there, beta 0 and beta 1. That's the intercept term. And the slope coefficient, y, of course, is the dependent variable. X is the independent variable. And then there is a term over there on the end, which is super, super important. We call that the error term. The authors seem to like to use the word noise. So noise, think of noise as just stuff that's out there that might be explained, it might be unexplained, but what it is an error term, because what we're trying to do is we're trying to gather this data for two variables and then make a prediction. And we know that whenever we make a prediction, that we're going to make that prediction with error. And so that term captures the degree of error. Of course, we don't want to come up with a model where we're going to predict the temperature, let's say today, somewhere along the East Coast on the beach. And we don't want to have a model that says, oh, today's temperature is going to be 412 degrees. That must mean that there's lots of an error term, because I'm pretty sure we don't get into the 400s with temperature. And so here's a classic picture over there on the right-hand side. There's the x variable on the horizontal axis. There's the y variable on the vertical axis. And of course, there is the line. So this is upward sloping, right? Doesn't have to be upward sloping. It could be downward sloping. Beta 1 could have a negative sign in front of it. And that slope coefficient, of course, didn't you learn this in your younger days? The rise over the run. Here's a great example. Look at the bottom. The more time you spend studying for CFA exams, the higher you would expect your score to be. And I tell students this all the time. I get this. Students say, oh, you know, Jim, I studied for 485 hours for this test, and I only made a 50%. And so my response is, well, okay, let's do some evaluation of your study time. Is it high quality time or is it low quality study time? But then couple that with your execution, your performance during the basketball game or the football game or the golf tournament or the exam. So that's why we've written in there you would expect your score to be. It doesn't guarantee that your score is going to be. So time spent studying is the independent variable, and then the score on the exam is the dependent variable. And so what does the CFA Institute recommend? You know, it used to be 300 hours. Now it's something a little bit higher than that for each of the exams. And so you can decide, let's go ahead and collect some data and say, all right, if I study for 400 hours, I may get an 80%. If I study for 1,000 hours, maybe I'll get a 90%. But that should make perfect sense. All right, how about this idea of a least squares criterion? So what I want you to do is I want you to look at the illustration on the right there, and just for a second pretend that those two lines, the red and the blue line, are not there. So we have x and we have y, and so we have lots of different outputs there from different levels of x. And so what this least squares criterion is going to do is it's going to pick a point somewhere in the middle and say, let's observe the distance between that point in the middle and each observation, and then let's go ahead and calculate the distance between those two. And that's what we're trying to do. Least squares criteria. We're trying to minimize the difference between each outcome and some hypothetical line. And so forget the blue line here for a second. Look at the red line. The red line, that pretty much doesn't describe the relationship between x and y. It starts lower and it goes through a couple of them, but then it goes way off up into the higher region and to the right. So the red line clearly is not a least squares regression line. But look at the blue one. The blue one, boy, it kind of goes through all of those. Some are a little bit above and some are a little bit below. But what that does is it will minimize the distance. And that's the idea of this. Linear regression calculates a line that best fits the observations. Now, you ought to say to yourself, you know, wait a minute, Jim, if I were to just see those 7 points on a graph, I could get out a ruler and I could go like this and like this, and I could draw a line myself just by visualization. And that's true. But when you do this visually with your ruler, you're probably going to make some mistakes. And that's what this least squares criterion does. It guarantees that you're going to have the best fit line. Least squares criterion. Now, the authors go to great lengths to tell you that at this point of least squares, they have the least squares method has identified the regression parameters, beta 0 and beta 1, such that the sum of the squared errors is minimized. That's what I was saying when I did this, when I went like that. Now look at that last arrow point. It is only the estimates, the beta 0 hat and the beta 1 hat. Those are those little funny things that are on top of it. And by the way, my colleagues and I, we used to make fun of each other when we were doing beta hat, beta 1 hat. That was just a funny comical thing in graduate school because we needed comedy to deal with all the stress. All right, how about the regression coefficient? So there's the slope coefficient and beta 1 hat. Remember, that's an estimate. And so we know this from our equity study days. Beta is always covariance over variance. Well, it's not any different here in regression analysis. So we're going to take the covariance between the two variables. One is independent, one is dependent, and then we're going to divide by the variance of x, and that is the slope coefficient. And of course, it measures whether or not one of the variables, when it changes, how much of an impact, there's that word that I used earlier, how much of an impact it's going to have on the dependent variable. And then the intercept term is kind of determined backhandedly. So look at that equation there. Beta 0 hat is equal to y bar, the mean of y, minus the estimate for the slope coefficient times x bar, which is the mean of x. So you kind of back into it to get that intercept coefficient. So let's take a look at an example, and we're addressing the part of the LOS that asks us how is it used to estimate regression coefficients. So the LOS doesn't say to go ahead and calculate these, but let's go ahead and do it, and then you'll be able to explain how. All right, so we have a financial analyst who holds the designation ARTH, estimate the regression relationship between annual inflation rate and the annual money supply growth rate for 6 countries. And so given the following information, calculate and interpret. So we're given covariance, we're given variance, and then we're given the two means. And so those are 4 important variables to go ahead and calculate. I can't imagine that the CFA Institute would ask you to compute all of those 4. All right, slope coefficient, this is a super easy one. So let's just take the 46 over the 239, right? We're given those back in the question stem. So if you do that, you get about 20%, right? 19.27. So let's read the interpretation over there. Annual inflation rate increases. Now notice that we have decreases in there because covariance can be negative. So make sure if the beta 1 hat coefficient is negative, then you have that inverse relationship. So here, annual inflation rate increases by 19 units whenever the annual money supply growth rate increases by 1 unit. And then the intercept term, we just go ahead and input that 1927 based on, what do we have back there? 35 and 933. And so we get, what is that, about 1.7%. And so the interpretation, this is important. Notice we have it in bold over there. Annual inflation rate, 1.7, when the annual money supply growth rate is 0. So this is an important conclusion. And that's how we always interpret the intercept term, that when the x variable takes on a value of 0, which in some regression analyses may be totally irrelevant and inappropriate, but in lots of them, like in this case, what if the money supply does not grow, that we're still going to have inflation? Wow, that's an important economics concept for a financial analyst to be able to make decisions. Now, you might know that the CFA Institute has lots and lots of LOSs scattered throughout, mostly level 1 and 2, some level 3, about assumptions. So whenever we're using a model, we need to figure out what are the assumptions. Because one assumption of a model might be, hey, we're assuming that the sky is blue. And that may be true during the day and when it's sunny out, but it might not be true for all different kinds of weather events. So make sure you understand these assumptions. All right, you ready? So let's repeat that first part. Relationship between x and y is linear, which implies that the independent variable is not random. So I want you to think about what that means, that if you have two variables that are random, if these are random and these are random over here, think of the Excel random generator function, and you have a column of a bunch of these numbers that are randomly generated, and a column of a bunch of these numbers that are randomly generated. There's probably no relationship between those two, right? So in order to have linearity between x and y, the independent variable cannot be random. However, the residuals that we talked about earlier, they must be random. So we have a big old X over here. So look at those residuals, or the error terms. They clearly have a pattern, right? Looks like a big old mountain there. So that's a pattern. And that would be a violation of that initial assumption. Now, another part of this is that the expected value of the error term is 0, meaning that some of the errors you're going to make above the mean and some of the errors you're going to make below the mean. Going back to my model of predicting temperatures, if every time you predicted the temperature in Virginia Beach, Virginia, that it was way above the actual temperature, what are the temperatures in the summertime? 90, 95, 85, maybe 100. But if every day you predicted 120 and what did I say earlier? 417 and 312. If you were always predicting above, then the model stinks. So what we want is to have, and don't ever tell your stats professors that you heard this from me. What we want to have, on average, half of the errors above the mean and half of the errors below the mean, and that means that they will cancel each other out. So the expectation of the error term is 0, and then the error term has to be normally distributed, and you can tell that by looking at a histogram. All right, let's get into some more serious assumptions here. And the good news for you guys here is that at this level, and in this reading, we just kind of skim over these assumptions. In later readings, we're going to get into some big problems caused by a violation of these assumptions. So what I want you to do is I want you to take a look at that check mark, that green check mark graph over there. So there's the best fitted line. And notice what's happening. The error terms, some of them are above, some of them are below, right? This is what I was talking about earlier. And they're on average about the same distance from that best fitted line. Boy, what does that mean from a statistic standpoint? That means that the variance of the error term is constant over all observations. This is known as homoscedasticity, and this is one of the underlying assumptions of this linear regression model. What we don't like, look at the second illustration, is when those error terms, they start out close, and then as we go way, way, way out to the right for that x variable, they start to spread out. They start to spread way out, which means that somehow in there that we're getting away from having a model that has any predictive ability. This is called heteroscedasticity. So we like and we rely on homoscedasticity. We don't like heteroscedasticity. And so how do we detect it? And what we're going to do is we're going to do the exact same thing that we did here in these two illustrations. plot the least squares residual against the independent variable, and then you'll be able just to visualize and tell. Now, there are some more advanced tests that we'll learn about in future readings, but for now, this is probably sufficient. Now, of course, this error term must be uncorrelated over all observations. So notice the expectations of the error term sub I and the error term sub j must be equal to 0. And if they're not, then you can go ahead and plot those just like before, and you see the little pattern that goes around there. So this is what we don't want. We don't want to be able to see a pattern. Let's go ahead and move on to this concept of the coefficient of determination. We already know what R is. R is the correlation coefficient. What do we know about correlation coefficients? They can be from a -1 all the way up to a +1. Well, if you square that term, right, you're always going to be between 0 and 1, right? You get rid of the negative. So when you square it, R squared becomes the coefficient of determination. And so what does correlation measure? It measures the magnitude and direction of a relationship. What does correlation coefficient squared measure? Well, I'm going to just repeat that. It measures the magnitude, but not the direction of a relationship, right? Because it's always going to be positive. But instead of worrying about the direction of the relationship, which we get that from correlation coefficient, right? What we do get is we get this idea of being able to explain the variability. All right, so let's go back to our simple linear regression model. So we're forcing all of these dots on our graph to be aligned. So we call that the best fit line. But those dots are still out there scattered. So what we want to do is we want to say, how much does the variability in one variable explain the variability in the other variable? And that's what R squared does. It is the percentage of the total variability explained by the model. Let me give you the extreme example of a correlation coefficient of 1 and a correlation coefficient of a -1. When you square that, you still get 1, right? Which is 100% R squared. And so if you have a correlation coefficient of 1, that must mean that the two variables look an awful lot alike. How about if they look identically alike? Well, then the variability in one can perfectly explain the variability in the other. And that's what R squared measures. So look at the second arrow point. A high R square explains variability better. If R square is 1%, then only 1% of the total variability can be explained. That sounds like a really bad model. An R square of 90% equals 90% of total variability can be explained. So look at that third bullet point. The higher the R squared, the higher the explanatory power of the model. Now the LOS goes and asks us to calculate, so we can do this in one of two ways. So if we have a model with just one independent variable, all we have to do is square the correlation coefficient. There it is right there. So that's a super simple way. Remember that. Look at that first diamond point. Works for a model with one independent variable. And I'm going to go ahead and skip to the next slide here. You don't have to worry about any of this stuff. With one independent variable, then just find correlation and square it. Now, if you have multiple regression, which is not the emphasis of this reading, but if you do, or if the CFA Institute says something like, hey, calculate it this way, and then go ahead and calculate it the second way, just to prove that you were correct, then you should be able to use the variation here. All right, so this is a simple ratio. So look at the second R squared equals. It's explained variation over total variation. And you can divide that explained variation in the numerator to total variation minus the unexplained variation. And then you can flip it around and do 1 minus that ratio as well. And of course, total variation down in the blue box is going to be, you ready for this? We have each observation, so that's yi of the dependent variable, right? Minus the mean of y, and then you square it. So you go from I equals 1 all the way up to n. I mean, n could be 6, or n could be 6,000, and that's the total variation. And then in order to determine the unexplained variation, you take the same y variables, but you subtract the y hat, the estimate from the model, and you square it. So of course, let's go ahead and come up with an example here. We have inflation rates and annual money supply growth rates for 6 different countries, which we had before. And so we come up with 2 different estimates there, right? Let's just go back here. So we're doing total variation and unexplained variation. And we're given those as 55 and 1096. And so the coefficient of determination, the R-square, is closest to. And I emphasize, go ahead and look at what we've put in purple there. Total variation minus the unexplained variation, and we put that in italics for you over the total variation, and there we get about 80%. Which leads us, this idea of something that's explained and something that's unexplained, it leads us to the following question. You should be saying to yourself, all right, Jim, let's go ahead and look more into this notion of explanatory ability. Clearly, there has to be something else, and that's what this something else is in this LOS. Describe the use of the analysis of variance, and then interpret and do some calculations. All right, so the analysis of variance is a statistical procedure to partition total variability. All right, so we have total variability that looks like this. And then we want to chop it into its 2 parts. And this is used, go ahead and look at that second arrow point, to determine the effectiveness of the independent variables in explaining the variation of the dependent variable. And so what can we conclude up to this point? We said that if we have a high R squared, well then we're pretty effective. If we have a low R squared, then we're not too terribly effective at all. But what we're doing in this analysis of variance is that we are investigating, we're layering it. So go ahead and look at the illustration there. We have X and Y. And so notice that we could have plotted all of the X and Y's on there, but we summarized that. We squeezed that into the red line, right? There's our best fit line. And so we take the mean of y, there's the mean of y down there at the bottom, and then there's the bullet point right on top of the line. And then there is the yi up at the top, and these are all of the different y observations that the analyst collected. And so notice that we have 3 blocks. We have on the left the total sum of the squares. That goes from y bar all the way up to yi. And then over here on the right-hand side of the green line, we divide those into the unexplained and the explained. The explained is below, the unexplained is above. And notice over on the dark blue box, total variation is equal to the explained variation plus the unexplained variation. And notice we're going to use these terms, the RSS and the SSE. So let's go ahead and take a look at the regression sum of squares, RSS. All we're doing is taking the yi hats, right? Those are the estimates minus y bar, and we're squaring it. And that's the red box over here, the explained sum of squares. So that's from y bar up to the line. How about the SSE, the sum of the squared errors? We're taking each observation yi minus that y hat sub I, right? And we're squaring it, and that's the orange box. That's the unexplained sum of the squares, right? And then, of course, if we add them together, we get the blue box here, the total sum of the squares. And this SST, sum of the squares total, is a measure of the total variation. And so I think, I'm going to go back here and do these three. I think that these three pictures, illustrations, are super important to be able to describe the use of analysis of variance, because this is exactly what we're trying to do. And I bet if you study these 4 illustrations for long enough, I mean, if you stare at them long enough, you can implant them in your brain so that you can call up those pictures on the exam. And just remember, blue box is total, orange box unexplained, red box is explained. And I think that takes you a long way into answering a handful of these questions. Now, this analysis of variance, the output is typically put in a table, and this is what the table looks like. So I'm imagining that you'll have an ANOVA table in the question stem. And so notice what you have down the left-hand column, sources of variation. So you have the explained and the unexplained and the total, and then degrees of freedom, and then the sum of the squares. So you have RSS and you have SSE, and then of course that is the total. And then you have the mean sum of squares. So all the way on the far right, you just have column, what is that, column 3 divided by column 2. And that's going to be important when we do an F test here in just a handful of minutes. All right, let's go ahead and ask ourselves the following question. Back in previous readings, we talked about standard deviation. So clearly there has to be a standard deviation of the regression model. So that's what SEE stands for, the standard error of the estimate. This is the standard deviation of the regression residual, and it measures the fit of the regression line. Remember, it's the best fit line, but it's not going to be a perfect fit, so it measures the fit. So what we want to do, see that third arrow point? The smaller the standard error of the estimate, the better is the fit of the regression line. Remember, it's not going to be a perfect fit. It's going to be a least squares fit. So there's the big old formula down there for the standard error of the estimate. And go ahead and scratch your head. I'm going to go ahead and scratch my head here. If you have to compute that, what you'll probably be given is a summary table. All right, so let's go ahead and, whoops, I went too far. Let's go ahead and work through an example here. So here's our analyst who holds the designation, Shah from before. There's growth rates in the money supply and inflation rate, 6 countries. So there we have countries A through F down the left-hand column. And here are the observed money supply growth rates. So there's our X variable. There is the rates of inflation. That's our Y variable. And so we go ahead and get out our software. You can do this in Excel. You can do it in Minitab. You can do it in tons and tons of software to estimate a set of linear parameters here. So remember, we're going to estimate the intercept and the slope coefficient. And so that's what that line means below the table. The linear regression equation has been estimated using this method of the least squares. So you have the intercept term of 1.7 and you have the slope coefficient of 1927, right? So there's our regression equation. So from this table, let's go ahead and try to compute this SEE. All right, so here we go. Ready? So here are the countries down the left-hand column. There's the X and Y variables. And then what we're going to do is we're going to form the predicted inflation rate. So let's go back up to the box there. I'll show you how we calculate that 38,217. So we take the regression equation, right? 1.7 plus 1927 times our independent variable of the money supply growth rate, which is X. So there's times the 11%, and that gets us the 0.38217. And if you want, you can go ahead and make sure that we've computed these correctly. Although we did this in Excel, so they're probably correct, going down the predicted inflation rate. And then what we need to do is we need to go ahead and compute the regression residual. So we're going to take yi, so there's the 0.04, and we're going to subtract the 0.38217. So that gives us our next column of 1783. And then we square those residuals and we get the 3179. So feel free to pause the recording and go ahead and do all this yourself. I can't imagine that the CFA Institute would give you a question like this and give you 59 countries, right? That sounds like way too many, but maybe 4 countries, or maybe, 4 variables somehow there in the sample over on the left-hand column. So it's probably a good idea to be able to compute each of the values in the column. And then, of course, over on the far right side, you're going to go ahead and sum those, right? The sum of those. And so there we did it all on the bottom. So take that 10, what was that number? Did I get all those decimals in there? Yeah, 106704 divided by degrees of freedom, right? 6 minus 2. So there were 6 countries, yeah, n minus 2. And then square root all that and you get 516. So there you go. What was that? What did we start with back here? Calculate and interpret the standard error of the estimate. So we just did that part of calculating it, and then as we went through all of the calculations, we did some interpretation. So there you go. Now remember, a few moments ago I said something like, hey, that column over there on the right of the analysis of variance table, that's going to be important when we get to the F-test and the F-statistic. Well, here's this LOS. So calculate and interpret the coefficient of determination and the F-statistic in a simple linear regression. So let's go ahead and first define the F-test. So look at that first arrow point. Determines how effective a group of independent variables explain the variation of the dependent variable. And this is going to be super important for us when we have multiple regressions, which is not the emphasis of this reading. Nevertheless, you can still use the F-test when we have one independent variable, but as you'll see in just a moment, the F-test and the t-test tell us the same thing. All right, so what do we want? A large value. If we have a large F, the regression model does a good job of explaining the variation in the dependent variable. So we went through a couple of those slides to determine the total variability and the explained and the unexplained. So what the F-test does is it kind of reaches out and grabs a hold of all that stuff and puts it into one output. Let's go to the other extreme. An F-statistic of 0 means, hey, wait a minute, Jim, I bet your model of predicting the temperature at Virginia Beach, I bet that has an F-statistic of 0 because it didn't explain anything of the variation in temperature. So an F-stat of 0 is no good. Okay. So there's our good old formula for F-statistic. So remember what I said earlier, we're going to use that stuff from the analysis of variance table to come up with the F. And essentially it's going to be the ratio of what you have on those two far right hand columns, the mean regression over the mean squared error. But let's go ahead and make sure that we have distinguish between k's and n. So k is the number of slope parameters to be estimated. So in our example, we have one independent variable, so k is 1. But remember, in multiple regression, you can have 2 or 10 or 500 if you really want to. And then n is the number of observations. There we go. Look at that diamond point. An F-test is carried out in the analysis of variance. And here's the hypothesis. It tests whether all the slope coefficients are equal to 0. Now, when you only have one independent variable, the F-test is identical to the t-test. Once again, I'll show you that here in just a second. So the null hypothesis with one independent variable is beta 1 equals to 0, and the alternative is that it is unequal to 0. So what we need are the SSE and the RSS, which we did earlier. And we're going to get a estimate of an F-statistic, and then we're going to have to compare it to a critical value. So there's a picture of the chi-square distribution. There's the F-test. So our critical region is all the way out in the far right tail, and that far right tail is going to be based on the analyst's selection of alpha. Do we want to be confident at the 95% level, at the 90% level? Or let's take some crazy notion. Do we want to be confident at the 0% level? Well, then my model of temperature at Virginia Beach, that's a great model if we don't want to have any confidence at all. All right, so this is what I was telling you. Let's look at a quick example here. So go back to our inflation and money supply. So we have one independent variable, right? So degrees of freedom for the regression equation is 1. The degrees of freedom for the error is n minus 2, so 6 minus 2 is 4, right? Yeah, I did the math right there, yeah. So if you add 1 and 4, you get 5. All right, so sum of the squares, you get those numbers there, and then the mean of the sum of squares, you just do that division, and using the above, calculate the F statistic at the 5% significance level. And there you go, you get 1890. So what did I say in an earlier slide? That the F statistic, we want something that's high, so 18, that sounds pretty high. But of course, we have to go back and compare it to the critical value on the F table. And so all we're going to do is run our fingers across the top. So that's K, right? So we stop at 1, run our fingers down. That's degrees of freedom, which is 4. And so our critical value is 7.71, and at that 5% level, right, 18.9 is greater than 7.1. So what do? We reject the null hypothesis that the slope coefficient is equal to 0, and we say, hey, this is good. The slope coefficient is not equal to 0, which means there is some kind of a relationship between the independent and the dependent variable. So you see, we're on the move here. We're trying to determine whether or not X can explain Y. And how have we done it so far? Oh, we find a high R squared. We like a high R squared. And then we do analysis of variance, which is summarized in this F statistic. And so what do we say? Hey, we like this model, right? Since we reject the null hypothesis, we can say, you know what? This model doesn't stink like your Virginia Beach model does, Jim. All right, so here's a little bit of a summary. We rejected the null hypothesis, right? So what we can do is we can go back and say, what about the t value? Notice that the t was 2.776. If we square that, we get 771. So look at the two circle points. Since the F statistic is the square of the t statistic for the slope coefficient, it infers the same thing as the t-test. Conclusion, F-test duplicates the t-test for a linear regression model with one independent variable. So here's the idea. If you get to a question with one independent variable, you can just do the t, which we're going to do here in a second, or you can do the F. You don't have to do both, although they will confirm the same conclusion. So let's go ahead and work on a t-test here. Hypothesis testing involves testing an assumption on the population parameter. So what we're going to do is we're going to take a look at these t-tests and look at maybe sometimes the intercept term, but that's not too terribly important to see if that's statistically significant. But the slope coefficient is going to be super important. And then we're going to go ahead and compute a confidence interval using that same t statistic. All right, so here's our equation for the t statistic. It's going to be beta 1 hat, right? This is the true, this is the estimate, right, from the regression equation, minus beta 1, which is the true slope coefficient, which is probably not observable. It's just something that we think is true out there. But a lot of times, beta 1 is 0. We're testing the null hypothesis that it's 0 in the idea that we want to reject that null hypothesis. And then we're going to divide by the standard error of the regression coefficient. So this is another standard error that we need to worry about. It's the variability in the estimate for the slope coefficient. All right, let's take a look at a different example here. 52 monthly stock returns. Using market index returns, so we get a slope coefficient of 2.5, standard error of 0.3. And so let's go ahead and put together a t-test to see if it is statistically significant. So there's our calculation. So 2.5 minus 0, right? What's our null hypothesis? Is the estimated slope coefficient significantly different from 0? Now, you don't have to make the null hypothesis statistically different from 0. Especially if you're forming a study like this. We have monthly stock returns on one side of the equal sign. We have index returns on the other side of the equal sign. We get a beta. That sounds like our measure of beta, our measure of systematic risk. So you might want to test that your portfolio is statistically different from 1. Because why do all this work if the beta of your portfolio is the same thing as the S&P 500 index? So a lot of times you say 2.5 minus 0, but sometimes you could say 2.5 minus 1 or any other number that you think is appropriate. So there you go. You get a test statistic of 8.33. And so we're going to look at the table over there. And by the way, on the exam, you probably won't get a gigantic table. You'll probably get, an abbreviated table so that you can look this up. Or the institute in the question stem may just say, hey, critical value is 2.09. But here, so we go down to, what was our sample size? 52. And so we're going to do 52 minus 2. There's 50 degrees of freedom. So run our fingers down. And by the way, notice that these tables truncate at, 10 and then 35 and 40 and then 1,000 and 500. So, I mean, think about this. The table could run from 1 all the way down to 1,000. There's no way the CFA Institute or a textbook could give you a table that's that big. And so you'll probably have degrees of freedom that fall directly on, that first column. And so then run your finger over to the 0.05, right? So the two-tailed test, 5%, so you get 2.09. So 833 is greater than 2.09. So we reject the null hypothesis and conclude that the slope coefficient is statistically different from 0. All right, let's predict one. And so what we're going to do is use our estimated coefficients to go ahead and predict a dependent variable. So let's go back to our example. So there's our regression equation with inflation and money supply. 1702 and 1927 is the slope. And so if the forecasted money supply growth rate is 20%, all we're going to do is take that value and throw it into the model. And there you go, 5.56. So what do we say? If the money supply growth rate is 20%, then we expect inflation to be 5.56. So that takes care of both parts of the LOS, to go ahead and calculate it and to go ahead and interpret it. Now we can also do a confidence interval for those predicted values. And so all we're going to do is take that predicted value, right, the y hat, and then plus or minus something. And we're going to take t, there's our test statistic, our critical value. And then we need the standard error of the forecast. And here's another formula that you need to worry about. Here's the variance of this predicted or prediction error. And look at the exam tip. It is unlikely that you will be asked to calculate. Rather, it will probably be given to you in the question stem, much like it is here. So there's our regression equation. The standard error of the forecast is, what is that, 7615. So let's go ahead and compute that interval. So first of all, you got to do the predicted value. So we already did that, the 5.56. Then go ahead and get our critical value. at degrees of freedom 4, right? Now we're only going down to 4, and then we're going over to the 5% on the two-tailed test because we're doing plus or minus, so that's always a two-tailed test. So notice what we're doing here in the middle of the page. Prediction interval is 5.56. That was our predicted value, plus or minus the critical value of around 2.7 times, you ready? So we need to go back here, times this variance of the prediction error, which, cross your fingers, hopefully will be given to you in the problem. And so you get, what do you get? 345 to 767. So there's the interpretation at the very bottom. We're 95% confident that the inflation rate will lie between, 3.5 and 7 2/3, let's say. Wow. So you ought to ask yourself the question, all right, we're predicting inflation, and that range there, 3.5 to 7 2/3, that sounds like a big range. So what do we want? We want a model that we can have much more confidence in a smaller range. Did I say that the right way? I think I did. All right, how about confidence intervals around a regression coefficient? All right, so what we've done so far is we have determined whether or not the slope coefficient is an effective regression parameter to explain the dependent variable. All right, so let's suppose that we say, yeah, we reject the null, and we say something like, okay, this is a good model. Well, let's go ahead and put together a confidence interval for that regression coefficient. So let's go back to my example. Suppose you're trying to figure out what the beta of your portfolios inside of a big portfolio or your individual stocks are inside of a portfolio. And so you get a beta of your portfolio and you want to see, okay, how accurate is that? So that's what we're doing here with this confidence interval. And so that's all we're doing there. We're taking our slope coefficient, plus or minus again, and we're going to multiply the critical value by the standard error of the regression coefficient. So here's a good example. Let's go back to our 52 monthly stock returns. What did we have? We had the slope coefficient 2.5, standard error was 0.3, 95%. So look that number up on the table, and we do that before, 2.009. So we're going to take our slope coefficient, which is 2.5, and do plus or minus times our critical value of it's around 2, right, times the 0.3 standard error. So we can be 95% confident that our estimate of beta, which is 2.5, that our estimate of beta will be between 189 and 3.1. And since that range does not include 0, we can conclude that the slope is significantly different from 0. So two ways to figure out statistical significance of the slope coefficient. I always thought this one was way easier when I was in graduate school. Let me go back here. Where were we? Did I miss it? Oh, no, there it is. Yeah, in graduate school, this is what we did. We always did T-tests and F-tests, no matter what our professors assigned us to do. We hardly ever, I'm trying to remember if we ever did this. We probably did, but it wasn't too terribly important. All right, on to the last LOS. You're probably familiar by now that the CFA Institute likes to add a final LOS that says something like, okay, you learned all this stuff up here, but what happens if something simple changes all the way up here? And so here's this last LOS. Describe different functional forms of simple linear regressions. And so what did we assume? Among those assumptions in the very beginning of the slide deck, we said that there is a linear relationship between x and y. Well, what happens if there's not? What happens if there's now this is Jim's term here, this is not a statistical term. What if there's a nearly linear relationship between x and y? Is there anything that we can do to make the nearly linear relationship into a linear relationship. And of course, there is an answer, and that's what this LOS asks us to do. Functional forms of simple linear regressions. What we can do is we can take the natural logarithm of one or both of the variables that will transform the relationship into one of linearity. So you ready for this one? The first one, and these are super simple now that I gave you that explanation. So the log linear model is you take the natural log of the dependent variable. So look at the model there, the natural log of y, and we still leave x over in its original form. The linear log model, we take the natural log of the independent variable and we leave the dependent variable in its original form. And then we can do both. We can take the natural log of both sides. Now, some good differences here. I want you to look at the second bullet point, the blue one and the purple one. In the log linear model, the slope coefficient is the relative change in the dependent variable for an absolute change in the independent variable. And then skip down to the purple, the absolute change in the dependent and a relative change for the independent variable. That's probably a good exam question. So I would memorize those 2 bullet points. And then of course for the log-log model, it's relative and relative. All right. So how do you identify, how do you select this? So coefficient, so high R-squareds are better, right? High F-statistic, and then standard error of the estimate is should be low. And I think that takes us through all of the LOSs. And so look, if you know those first 3, right, describe and describe least, and then the assumptions, then the rest of these things, you know, they kind of make sense, but don't eliminate any of these LOSs from your studies.